the attempt. I'm very happy that the talk last night, or yesterday evening, has something to do with matrices, because at least this makes this talk a bit relevant. This is a talk about tropical matrices and an attempt to understand the basic structures of matrices, matrix groups, and the tools of matrices in the tropical setting. So I had a bit of a problem setting this up on the computer, so you're going to see some interesting notation here, but I hope not too much. So I put although I wrote supertropical domain, obviously you can form matrices over any semi-ring, because they're defined just in terms of matrix product, and matrix addition has nothing to do with minus. And so we're going to take that point of view. We write, this is a standard notation for a matrix. And so, of course, there's a problem about the determinant of a matrix. We're going to get to that in quite a bit more detail. But let's say a matrix is good, it's non-singular. If when you view the formula for the determinant, the sums, you have the sums of these products along permutations. If one permutation dominates all the other permutations, in other words, the product of the elements along one permutation is bigger than all the others, then we're going to say that the matrix is non-singular. And that's the kind of matrix that we're interested in. The singular matrices are also very interesting, but the non-singular matrices play the role of non-singular matrices in the usual matrix theory. So, this is like one of the examples of the interesting notation. I meant to have this line over there, but I didn't notice it until about 5 minutes ago. Okay, so you have this idea of a dominant permutation. If this is greater than all the others. I'm going to talk about this notation quite a bit in the next few minutes. And, but the idea is that it's the greatest one. Okay, so this is what I said before. If it's a single strictly dominant permutation. And obviously, well, I don't know if obviously, but you want SLN to be those matrices such that this dominant track gives you the product of their entries is 1, because that's what SL is. It's determinant 1. And so our object today is to understand SL as well as we can, and then one could go on to other matrix groups and further. So, of course, the basis of what one does is through this Puiseux evaluation, and our objective in general over the last few years has been to look at the level of G, at the target of evaluation. And that's where all this so-called supertropical algebra resides, is in this target of evaluation. So, of course, one has this ambiguity that if two Puiseux series have the same value, then the lowest term might cancel when you take the product. And that's where this whole thing of ghosts comes in, because we want to somehow say that there's an uncertainty in the sum when they have the same value. So we're incorporating that into our algebraic structure so that we can study it directly algebraically without words. Okay, so the way we do this is we take two copies. We have the tangible copy, which is what we're interested in. That's, well, there's a bit of ambiguity in the notation because I had us going to G here, but the copy of G that we're interested in, we're renaming T. And then we have this other copy, which we call the ghost copy. Okay, and so we're going to have the formal union of G and T, and that's going to be our semi-ring R, which will be defined in a minute. And we're going to have a projection of R onto G, which is the identity on G, and which is the isomorphism from T to G. Since R is T union G, that defines the entire projection from R to G. Okay, so this is written, oopsie. Oh, this is just some propaganda. Yes? Oh, minus infinity? Well, you could put in minus infinity if you want. I prefer not to. I prefer to look at the toric situation. But with matrices, actually, we probably want to have minus infinity. But as long as you brought up that issue, minus infinity, I mean, as everybody has come across here, minus infinity as the zero element does not play as significant a role as it does in usual structure theory of algebra. And when one deals with it abstractly, it's sort of an interference. One always has to have a separate axiom for minus infinity, such as minus infinity times times every element is minus infinity. And so it's simpler for me not to talk about it. But anybody who wants to join minus infinity, of course, you can join minus infinity anytime you want. Okay, so exactly. Right, exactly. Oh, I should have put K star. Oh, yeah, okay. That's, okay, so, this is what I was saying before, that you have a kind of fuzzy element that you don't really know what it is. And here's the structure. So you have this union where you could put in 0 also formally if you want. And when the value of A is greater than the value of B, you take A, so it's the max that way. But when they have the same value, then you move from the tangibles to the ghosts. You move from the concrete to the fuzzy, essentially, because you don't know really what this is. Okay, well, that last sentence was philosophical. I mean, you know what it is formally in the structure. It's in the next level. It's in the ghost level. So, also, I'm not sure if I wrote down products, but when you take the product of two elements in T, that's fine, that's in T, so T is a monoid. The product of two ghost elements is ghost. The product of the ghost element and the tangible element is defined to be ghost. In other words, A times B ghost is AB ghost. You use the isomorphism to identify the two. So, by the way, this was defined by Zur in his thesis, essentially, in his doctoral thesis. So that makes the ghost an ideal, because you multiply ghosts by anything and you get a ghost. So I'll get to that in a minute. Just notation, we'll write, just to shorten the notation a bit, we write A nu for nu of A. And, okay, and we have this order that we take from G. G is given to be ordered, of course, because that's what we start with. Okay, so you have these tangible elements, which is a monoid, and you have the ghost elements, which are unideal. G itself, being isomorphic to T, is also a monoid whose unit element is one ghost. which is 1 plus 1. But viewed, we call this E. But inside all of R, it's an ideal. That's pretty clear. So it's because E is an idempotent. E is also multiplicative idempotent, both additive and multiplicative, which is strange. Okay. By the way, if one's talking about F1 geometry or something like that, the F1 here actually has 2 elements, has 1 and 1 ghost, right? Because you always apply the new structure to take it across. Okay, so intuitively, we want the tangible elements to be what we work with, and we have this rule, which is crucial in everything. Another maybe philosophy or intuition is that this rule is the way you look at corner roots and things like that. When something occurs twice, you move to the ghost level. Okay? So you stay in the tangible level until something occurs twice, and then you go to the ghost level. Okay. So then this relation seems to come up a lot, that instead of equality doesn't quite work well in this theory most of the time. This works much better, even though it's not symmetric. But this relation says that, you see, when B is tangible, you cannot get to another tangible element by adding a ghost, because if the ghost is dominated, then that would mean B equals A. And if the ghost itself dominates, then it turns the whole thing into a ghost. So this relation generalizes equality in the sense that when B is tangible, you have equality. But it seems to work much better in the theory. We're going to get to that. Oh, another piece of intuition here is that ghosts, in a sense, replace 0 in the structure. In other words, anytime you have a theorem in regular algebra that something equals 0, well, let's say 90% of the time, you want to replace it in this language by saying that it's a ghost. In other words, it ghost surpasses 0. So in other words, instead of saying it equals 0, you say it ghost surpasses 0. Okay, so please try to bear that in mind, because this is going to come up over and over again. Okay. So now we do the same thing for matrices. So I think that's pretty clear. You look at each entry of the matrix and see what happens. And so if each matrix surpasses B, then if each entry of the matrix surpasses B, then you say that the matrix surpasses B. In this sense, that it's either equal, if the entry is tangible, they're equal, and or else it could be a bigger ghost. Okay. Okay, so now we're set up for essentially translating everything from regular algebra to this structure, except that the interesting thing is only 90% of the things work. So it's the extra 10% that sort of makes life interesting. But first of all, we define the determinant. What's the determinant? You don't have -1, so you use the permanent. And but we're going to call it the determinant anyway, because it behaves like a determinant. Okay. So this is what I said before. If the determinant is tangible, I said it in a different way before, but in this language, it's the same thing. Because you see, this will be tangible if and only if there's one specific permutation which dominates. Because if there are two, then you sum them up and you get a ghost. Okay, is that clear? In other words, you take all these tracks. If one dominates, then this is tangible, and so it's singular according to what we said before. If two dominate, then the sum is that plus itself again, which is a ghost. Okay, and so singular.
A is tangible entries here.
That's right. It doesn't have to. I'm just simplifying the discussion. But in fact, it could have arbitrary entries. But of course, if it has a ghost entry, then that track will give you a ghost value. And so if that's involved in computing the determinant, it will automatically be a singular matrix. So if you want a non-singular matrix, you have to have enough tangible entries to have the leading track be tangible. Yes?
Another question, what do you expect if you have tangible element plus a ghost element? This gives you a ghost element?
If you have a tangible plus a ghost element, the one with the larger value dominates. Thank you for the question. So, so 3 plus 2 ghosts is 3. 3 ghosts plus 2 is 3 ghosts. It's the larger one that dominates. But 2 plus 2 ghosts, I say 2 plus 2 is 2 ghosts. And 2 plus 2 ghosts is 2 ghosts automatically. Okay, so yeah, that's the thing. The larger value dominates. I should have stressed that. Okay. So, now this is a very important matrix, which sort of is like in the 10% that I said that makes life interesting. So the determinant is, when I write, there's a question of what 1 is and what 0 is. When I write examples, 0 will be the unit element. Okay? So this is like in the max plus setup. So what's the determinant? The determinant is minus 1 times 1 is 0, plus minus 1 is 0. So this, so I should have written 0 is 1 of A. I mean, this 1 is a different 1. This is the unit element of A is 0. Okay? I just forgot the subscript here. So its determinant is the unit element. This should be an SL. Is there any question about that? Because this is very basic. This should be an SL. But when you take its square, its determinant now is 1 plus another 1, or times, plus another 1, which is 1 ghost. So you see the determinant of A squared is not the determinant of A, which I'm sure everybody who's worked with matrices in the max plus has come across examples like this. But the point is that it's ruined because of the double entry in the determinant. So, so it ghost surpasses A, even though it's not equal to A. It ghost surpasses the determinant of A. So what we have is the determinant of A squared ghost surpasses the determinant of A. If this were tangible, if A squared were singular, then it would have to be an SL. That would follow from the next theorem. So this is what we have in the supertropical structure. And this is what I meant, that you often replace equality by this. This is true. And so if AB is non-singular, then in fact you will have equality. But the previous example from the previous slide shows you need not have equality. Are we together on that? So SL is sort of a monoid in the sense, I don't know if you call it quasi-monoid. When you have the product of two entries of SL being non-singular, then the product is an SL. But it could be singular. So you have to take some sort of closure. You have to take a ghost closure or something. Okay. So the next question would be, if AB is non-singular, is BA non-singular? Because after all, you have equality when AB is non-singular. So this is a cute example. It's even false when B is AT, you take this, of course, this example is based on certain relations among the entries, but I just took a particular example here. So the transpose is this, and this is non-singular, and the determinant is correct. The determinant has to be 5 times 5, because that's the determinant here, which is 10, which in fact is 10. But if you take ATA, it gets ruined for some reason. And the determinant isn't 10, but its ghost exceeds 10. Okay? So that's a strange thing. I don't really understand. I mean, one can look at the properties of the coordinates, but I don't understand really why that happens. Okay. So the next thing to do with the matrices is to take the adjoint, right? And that's basic thing in matrix theory. And so there's a counterexample to this, but this is pretty clear-cut. I mean, it's an easy calculation. This is harder. If AB is non-singular, then in fact you have what you would like to have from algebra. So again, when you wind up with non-singular matrices, things work out. But this is, the proof is not completely difficult, but it's not completely trivial. This is a very nice theorem. This is a harder theorem because it involves equality. I said that ghost surpasses usually comes pretty easily, but the other direction, that both of these are equal, requires some graph theory, or whatever this is, the Birkhoff-von Neumann theorem. Okay, so this is really a review of things just to give you the idea of what's going on. And this is a few years old already, but and then, of course, you have these different kinds of matrices, and it's well known that the only truly invertible matrices are generalized permutation matrices. Right? I think that's known like about 40 years or something like that in Max Plus. And of course, permutation matrices are obviously invertible because you just invert the permutation, and diagonal matrices are obviously invertible because you just invert the diagonal entries. So these two are obviously invertible, and the interesting thing is that you don't get anything else, really, except for their products. Okay. So because of that, because the theory of invertible elements in this setting is pretty trivial, we want to have a different notion of invertibility because we want it to be an interesting concept. We don't want it just to be, a 5-minute exercise. So, so this involves the adjoint. So what are we going to, first of all, if we can't invert something, we want to almost invert it. So we define this as a, so permanent and determinant are the same thing in our, today, well, the next 15 minutes at least. But, so quasi-identity, what are the properties of identity matrix? It's idempotent, has determinant 1, and then the philosophy is that we replace zeros by ghosts, so it'll be the identity on the diagonal and ghosts off the diagonal. Okay. So, in fact, you can deduce that from the first half of this definition. Okay. And then you have this very basic fact that when you multiply a matrix by its adjoint, you get the determinant permanent of A times some quasi-identity, which we call IA. And of course, you could do that in the opposite direction, but you might get a different one. You get a quasi-identity, but it might not equal IA. Uh, in the nice situations, it does, but there are counterexamples. Okay. But this is always true. If you do this other direction applied to the adjoint of A, then you get the quasi-identity of A. So there's a kind of duality here. Okay. So this leads us to define a maybe quasi-inverse. We wrote it A nabla, which is the adjoint divided by the determinant. Because by definition, then A times A nabla is IA. I won't go into this because this is another subject, but you could use the nabla to solve matrix equations. Okay, it's quite interesting, but it's in a different direction. So this is true. A quasi-identity is its own quasi-inverse. And for a while, we thought this might be true, but it's not hard to dig up a counterexample. But if you do it 3 times, you repeat. So, and then you keep on, any time you do this more than twice, you get repetition here. So you have a kind of closure operation. And probably it's correct to only analyze these closed matrices. They have A nabla has a lot of very similar properties to A. But anyway, that's an aside somewhat. An invertible matrix is an easy exercise to show that the nabla is the inverse. And so this closure is itself. But in general, if the matrix is not invertible, then one has it. Okay, this also is somewhat old, but it's one of my favorite facts about this, that if you define a polynomial, and then again, you use ghosts instead of 0, so say something satisfies the polynomial if its value is ghost, then in fact, if you take the characteristic polynomial, where of course we have to use plus instead of minus, any matrix satisfies its characteristic polynomial. So you have a characteristic polynomial of a matrix in this supertropical situation. Oopsie. Okay, and then you can define eigenvectors. And again, this isn't really our focus for today, but in the usual matrix theory over the max plus, you often have just one eigenvector, the largest one. But in the supertropical situation, because you have to have equality, and equality doesn't work in general, but in the supertropical situation, we're going to define eigenvalues with this instead of equality, and then you have n eigenvalues, and they're exactly the roots of the characteristic polynomial in this ghost sense, that fa of that thing is a ghost of the character of the eigenvalue. Okay, and then again, same principle which we've used a dozen times already. You define dependence by saying that some tangible linear combination is a ghost, and then you can define a rank, and these 3 numbers are the same. The row rank, the column rank, and the submatrix rank. In this sense, they're all the same. There are many definitions of tropical rank, so this is just one of them. But it has a nice characterization. Okay, here's part of the 10%. Actually, for 2 months, I thought I'd proved that these that when the characteristic polynomial has distinct leading factors, then the eigenvectors are independent. And then I think on the way back from an opera, it came up with, we were on the bus or something, and this example turned up. If you take this matrix, its roots are, there's 4 distinct roots. But if you compute the eigenvectors, you get something a bit sloppy, and the determinant of that matrix is a ghost. There are two tracks which are equal. Don't ask me which ones, I forgot. But, anyway, and actually, Adi took this example and analyzed why it's a counterexample. Okay, it's a way that you have to look at the way the different tracks interrelate, and there's a specific criterion which will determine when this is tangible and when it's not tangible. Okay, so let's go to SL. So now we're essentially going to what I wanted to talk about today. Since this is not a monoid, we have to close it in some way by taking, instead of taking the determinant being 1, that it ghost surpasses 1. So I hope I've convinced you by now that this is a natural thing to do in this particular language. Sorry? This is the real one. I mean, the algebraic one, the multiplicative union. Yeah, I'm going to have to go through this and make the ones fancier or something like that. Oh, you're right, because I was saying 0 before. Yeah, this one is the 0. Okay, I mean it's the unit element in the it's a unit element. Sorry, I don't hear you. It's the identity. It's the semi-ring multiplicative identity. Sorry about that. Okay. So it's the same thing that defines SL. So in other words, you want the determinant of A to be the unit element when A is tangible, and when A is non-singular, it could ghost surpass it. Did I express that okay? It's crucial, so I'm hoping I'm saying it in a clear way. It's essentially the ghost closure of SL. If you multiply, it's the monoid that's generated by SL. Because when you multiply 2 matrices of SL, either they're in SL or they ghost surpass it in the determinant. Okay. Now, so we want to view this in terms of maybe a union of simpler monoids or something like that. So what we want to do essentially is we want to analyze SL, understand how the matrices, what their properties are, how you can decompose this. So, but we can't, okay, so there are 2 approaches. One is to decompose it into a union of honest-to-goodness monoids. In other words, one where the multiplicative identity is the identity matrix, the usual identity matrix. And the other, but that doesn't work so well. We're going to get to that. Because the identity matrix itself is so limited, you can't get to it. You can only get to it from generalized permutation matrices. So when I say you can't get to it by inverting matrices usually, because there's so few invertible matrices. So we want to do something else normally. We want to use these quasi-identities in the structure because they come up so naturally with the adjoids. It seems only fitting that they would come into this structure too. But it doesn't quite work but it works for this kind of element. Now, this means that A is the quasi-identity times A. So this condition also is quite natural condition. And it's also looks pretty symmetric. And also, if you do this twice, if you take A nabla A, you get back to A nabla A. So, and you keep on, because you keep the quasi-identity, remember, one of its properties was that it's multiplicatively idempotent. So every time you multiply, once you start this process, every time you keep on multiplying by A nabla, you don't do anything. You don't change anything because you're just taking A nabla squared, which is A nabla. So, so once you get to this level, then everything works fine. And that's what I meant in this statement. Okay, so so we might want to replace A by A nabla A. Let's see what happens here. Okay, so we, I guess I changed the notation here a bit. I wrote IA left for A nabla and IA right for A nabla A. And they don't have to be the same. If they are the same, we call A reversible. And then for any non-singular matrix A, we have a bunch of monoids. Well, they're semigroups, actually. They're sort of naturally defined semigroups. I'm like, this kind of construction comes up all the time in algebraic structure theory, in ring structure theory, let's say, except we're doing semi-rings here. I'm sure it's semigroups, people have looked at this. And then the intersection would be, we call SLAN. And for quasi-identities, if A is a quasi-identity, the definition is a bit simpler. Okay? And one can check that for any regular element, any nabla regular element, that actually belongs in SLAN. In general, A need not belong into SLAN. You have to go up one level. But what you get here is that this is a subsemigroup. Oopsie, this should have been right unit, not right inverse. Okay, so please read unit here. So it has, this is sort of cute. It has a left unit element and a right unit element, but they need not be the same. And that almost contradicts something one learns in the first week of abstract algebra, but it doesn't quite. I mean, I looked at it for a few minutes, and because, well, if you try to do the exercise from that course, you'll see why it doesn't work. But if it's reversible, of course, then they're the same, and then they're unique. And then it's unique. So any reversible element of SL defines this monoid. And if it's also regular, then it belongs to that monoid. Okay, so that gives you at least the decomposition of SL, which includes monoids, kind of principal monoids or something like that, built from reversible regular elements. And as I said, the condition of regular is quite mild. You can get from any element to regular element just by going to A nabla A. Reversible is a bit more subtle, but it includes all the quasi-identities. Okay, so this is, yes? You don't know. I left times I right? I don't know. It could be quite complicated, I think. maybe, maybe somebody, maybe you'll have an idea about it, but because the thing is reverse, and so I don't understand how the product works. I mean, it would be A nabla, A, right? That would be because A nabla is one of them, and A nabla A is the other one. I don't know what A nabla, A nabla A is. No, one is in the left, one is in the right. It's not symmetric. You're right. That's a thing that one should ask. I mean, there's probably some theorem there. It's just that I don't know what it is. Okay, but yeah, I mean that's an excellent point, though. I mean, like the relation between the quasi-identity and the stool. There should be something. Okay. So, what if we want to go to honest to goodness subordinates? Where you have the same unit matrix. Well, there are all sorts of counterexamples, but one can say something, and it's probably of interest. My personal feeling, well, I won't say what my personal feeling is, but so this is an alternative thing, which of course the theory would be more precise because you have subordinates with the same unit element, and so we'll say I think that I'm not familiar with the matrix terminology so well, but my colleagues say that these are the correct terms. A matrix is definite if the dominating permutation is the identity such that all the diagonal entries are 1. And this is the unit element again. Whenever I write 1 in a sentence, it means the multiplicative unit element. And if each of them is, if each of the off entries is less than 1, then you call it normal or strictly normal. See, the problem here, the reason we're having all these definitions is that you could have a situation where the non-diagonal track has large entries which are balanced by small entries, so the product is less than 1. And that can produce a whole slew of counterexamples, because when you multiply matrices out, then all of a sudden you have a large number of large entries off the diagonal, which might ruin the matrix or ruin its chances of being non-singular. So that's why we have this condition that all the off-diagonal entries are bounded by the diagonal. And if you don't have that, the theory, what I'm going to say doesn't work. Okay. So a strictly normal matrix is always non-singular because the determinant is just by the diagonal. Normal matrix can be singular because you can have other entries which are equal to 1. And again, this is the Picasso version of writing the determinant. Okay. Or, I don't know, Picasso, maybe somebody else. But, okay, so if you have a definite matrix, oopsie, this should be a non-singular. If you have a definite, no, this is right. If you have some entry, I said that some of the entries could be large if it's a definite matrix. And then if you pick that up in the permutation, if you take the same permutation, then this will be ruined. This will become a singular matrix. So that's why you have a problem with definite matrices which are not normal. If you remember what the definite is the general one, and normal is the specific one. So, in fact, that lemma shows you, if you maneuver it, that any non-singular submonoid, honest-to-goodness submonoid, containing the invertible elements, that's the permutations essentially, and generalized permutations with, where the diagonal has determined 1. That cannot contain a non-singular matrix other than one of this form. In other words, once you start with the invertible matrices and build it up, you're going to get bad matrices. I'm sorry. If you're inside a monoid, if you're inside a submonoid, you can only get matrices involving normal matrices. The non-normal matrices cannot arise in submonoids. Okay. So now here is a list of some of the submonoids, honest-to-goodness submonoids. Certainly, the subgroups are submonoids, diagonal matrices. These should be the tangible diagonal matrices. Upper triangular matrices are monoids. This is to cope with that example where a squared is singular. If a to the n factorial is non-singular, then you keep on going and you'll never get a singular matrix. All the powers of a will be non-singular. Okay, so that's, and then this is this last thing that I was talking about. So in a sense, this is the most interesting. These are pretty trivial. This is, if a to the n is strictly normal, then in fact, you'll get a non-singular monoid. And we can extend that. So we're going to talk about this set of all strictly normal matrices. And this is a monoid. It's not hard to see. But what's maybe more interesting is this. So if you take its conjugates, or similarity classes, I guess you call it, with respect to permutation matrices, you still wind up with strictly normal matrices because the permutations don't, now the main track won't be on the diagonal, it'll be off the diagonal. So it won't be strictly normal in that sense, but it'll have one main track, and then the others will be dominated. And you multiply those together, and again, you keep on having one main track. So this is a monoid. And in fact, it's a maximal submonoid. So this monoid has considerable interest. This is the permutation closure of the monoid of strictly normal matrices. Permutation closure being that. Okay? So it's maximal. It's not the unique maximal one, because we had that other list. For example, the permutation matrices themselves will not, the triangular matrices will not belong to this. And so it's not the unique maximal submonoid. But it's very interesting, I think. Oopsie. Okay, well, I guess that's all the slides I made. There's one other point. So what I tried to do in this discussion was to set out the basic properties of various matrices of determinant 1, SL. Of course, one could define other algebraic objects. I don't know whether to call them monoids. They're really not strictly monoids because of this problem about multiplying and getting singular elements. But for example, what about the set of matrices where A transpose is A nabla? So that would be like a unitary group, or a unitary quasi-monoid, whatever. Or you could have quadratic forms. You can go on and look at the various analogs. That's one thing. One thing which Adi did in her dissertation was to try to analyze decompositions or factorizations of elements of SL, because, of course, SL contains the elementary matrices the way everybody learned them in school. And so SL over a field in the classical situation, of course, is generated by the elementary matrices, and that's used a great deal in the study. So this is false, and I'm probably sure that anybody who's worked with the matrices of the max plus has come across this, that the elementary matrices do not generate I think 2 by 2 they do, but 3 by 3 already they don't. And so she has been looking at that, and my guess is that if one wanted, I was thinking of talking about this in greater depth today, but then I thought that these are more concise results. I would imagine that if you want to develop a K1 theory, you would build on from that, and that essentially the theory looks more like K1 over a ring and not K1 over a field. And because you don't have this basic decomposition or this basic factorization that is the starting point of the theory of K1 over a field. Okay, so I guess that's just about everything I wanted to say. Thank you.